Hello and welcome back. This session is about set binary operations. We have talked quite a bit about sets. We have not yet officially covered set basic binary operations such as the union and intersection of sets. And that's what this session is all about. Now let's talk about operations that take set inputs and produce set outputs. Thus far, we have talked about operations that are defined on sets of numbers. A unary operation on a set of numbers takes a single number input and produces another number that's another element of that same set of numbers. And a function was an operation if it was closed on all elements of that set. Now consider a unary function that takes a set argument. We know that every set in the context of our study is an element of the power set of our universal set. The universal set is the set of all possible elements in our context of study. So if we're talking about real numbers, sets of real numbers are always elements of the power set of real numbers. Therefore, we can define our domain and codomain in terms of the power set. So for a unary function, our domain is the power set of our universal set, and so is our codomain. For a binary function, our domain is a Cartesian product of the power set of our universal set with itself, and our codomain is the power set of our universal set. So we have mappings in the case of a binary operation that takes set inputs that are elements of the Cartesian product of the power set with itself. These are tuples, these are ordered pairs in which each element of the ordered pair is a set itself. The set union is an example binary operation that takes two set inputs and produces another set as output. The union is related to the logical OR operation as follows. The union of sets A and B equals the set of elements X, given that X is an element of A or X is an element of B. So we get the set of elements that are either in the left operand set A or in the right operand set B. An example, if we have on the left the set of numbers 1, 2, and 3, and on the right we have the set of the numbers 2, 3, and 4. Our results set has the numbers 1, 2, 3, and 4. We do not have any double counted elements as defined for the definition of a set. There are no double elements in sets, and we have the elements on either side of the union operation, the elements that are in either of the two operand sets. Now, if we do union multiple times on a collection of sets, where we'll use the collection notation A subscript I, we can write that with this big U notation that you see at the bottom of the slide. So big U notation simply means I'm applying the union operation multiple times on a group of sets as you see as indexed, shown on the slide here. The set intersection is another binary operation that takes two input set elements and produces another set as output. The intersection is related to the logical AND operation. It's the set of elements that are common in both operands. So the intersection of sets A and B is the set of elements X, given that X is an element of A and X is an element of B. It's the set of common elements where X is an element in both A and B. For example, if on the left we have the set of numbers 1, 2, and 3, and on the right we have the set of numbers 2, 3, and 4, the set of common elements, common numbers in these two sets is the set of numbers 2 and 3. Now, just like we saw with the union, on the intersection we have the big intersection notation if we have multiple sets. If we apply the intersection operation multiple times, on sets A subscript I, then we can use this big intersection notation with the index as shown at the bottom of the slide. Now let's look at the properties of the union and intersection operations. We'll see that these are the same as the logical OR and AND operations respectively. Specifically, let's look at idempotence. A union A is A. Remember, this was the set of elements that are in either the left or the right operand, and since those are the same, it results in the same set, and sets do not double count elements. So A union A is just A. Now, the intersection A and A is also A. Remember, it's the set of common elements, but A has all elements in common with itself. So the intersection is idempotent as well. The other interesting property is the distributive property of the union over the intersection and vice versa, just like we see with the logical AND and OR operations. These properties together with a few other requirements mean that the algebra of sets is a Boolean algebra. It's an idempotent Boolean algebra. Now let's look at an example that combines a number of the concepts that we talked about. Let's say the universal set is the Boolean domain, then the power set of the Boolean domain is the set where the elements are the empty set, the set with just the 0 number, the set with just the 1 number, and the set that has the entire Boolean domain, the numbers 0 and 1. This power set is the set of all possible selections of Boolean numbers. Now, those are going to be inputs to our union and intersection operations. Now, if we define a set that contains the element 1 as true, and if it doesn't, so it's either only got the 0 element or the empty set, then we say it's false. If we define true and false that way, we'll see that the union and intersection operations completely mirror the Boolean logical operations in this example. Let's summarize the session. We saw the power set as domain and codomain of operations that take set inputs and have set outputs. We then covered basic binary set operations, the union and intersection operations. And we saw that these operations have the same basic properties as their corresponding logical operations. And that as a consequence, the algebra of sets is a Boolean algebra.